Okay, so in this problem, a perspective view of a flat surface with some area A, which is 3 centimeter square, is given, and this is in a uniform magnetic field. The magnetic flux through this area is 0.90 milliweber. We need to calculate the magnitude of the magnetic field and find the direction of the area vector. So our target variables are the field magnitude and the direction of the area vector. So let's sketch, this is the perspective view. Let's sketch the edge-on view of this problem. This is the direction of the magnetic field, and this is the area. This is making 60° with the B, and from here it is making an angle of 120°. This is 30°. So here, okay, because the magnetic field is uniform, we know B and phi are the same at all points on the surface. We can simply use this equation. Phi B is equal to BA cos psi, and our target variable is B. The area is given, the direction of A is perpendicular to the surface, so it phi could be either 60° or 120°. But we know phi B and area, this flux, magnetic field, and your area are all positive quantities. So cos phi must also be positive. This rules out this 120. So we only, the angle we have is 60°. And so it's easy to find now. The field magnitude, which would be phi B over A cos phi, and we can simplify. Three to 10 raised to the minus 4 meter square into cos 60° equal to 6 Tesla. And the area vector is perpendicular to the area in the direction shown in here, this one. So let's move to the other topic, which is about the motion of charged particles in a magnetic field. When a charged particle moves in a magnetic field, then a force, it experiences a force. So if a particles move in a circle at a constant speed, the net force acting on the particle is constant in magnitude and point towards the center of the circle, and it's always perpendicular to the particle's velocity. You can think of a stone tied to a string and whirled in a circle on a smooth horizontal surface, or you can also think of a satellite moving in a circular orbit around the earth. When a stone is tied to a string and drilled, the tension in the string provides the necessary force and the centripetal acceleration. And in the case of satellite, the Earth's gravitational attraction provides the force and acceleration. Here, a beam of electron is ejected into the chamber with some electron gun, and the electrons enter in the plane of the page and here it's here, and a particle with positive charge q is at point O moving with velocity v in a uniform magnetic field. We only choose one motion of one particle, and it is directed into the plane of the figure. The vectors v and b are perpendicular, so the magnetic force F is equal to q v cross b, which has magnitude F is equal to qvb, and our direction is shown towards inside. Here, this is the force the particle is experiencing. The force is always perpendicular to v, so it cannot change the magnitude of the velocity. It only changes the direction of the velocity, or we can say that the magnetic force never has a component parallel to the particle's motion. So the magnetic force can never do work on the particle. And this is true even if the magnetic field is not uniform. Motion of a charged particle under the action of a magnetic field alone is always motion with constant speed. And this principle is shown here in this figure. The magnitudes of both force and velocity are constant. At points such as P and S, the directions of the force and velocity have changed, but their magnitudes are same. The particle therefore moves under the influence of a constant magnitude force that is always at right angles to the velocity of the particle. And we can relate these conditions with circular motion, because the particle path is a circle and it is moving with a constant speed v. And by applying the concept of the circular motion, we know that centripetal acceleration is v square over r, and the only force acting here is the magnetic force. So from Newton's second law, we can over r. Here m is the mass of the particle and r is the radius of the circular path, and we can find the radius, which is qb. So this is the radius of a circular orbit in a magnetic field. So this is the radius of a circular orbit in a magnetic field. We can also write it as, so here p is equal to mv is the magnitude of the particle's momentum, and the time period the period t, the time for one revolution, is equal to the circumference divided by the speed, and we can find it from this, which is 2 pi r over v is equal to 2 pi over v into this equation mv over kv, and this becomes 2 pi m over q into v. The frequency, the number of revolutions per unit time, f is equal to 1 over d, and this becomes qv over 2 pi m. And you can also find the angular frequency of the motion, which is omega is equal to 2 pi f, and this becomes qb over m. These quantities t, f and omega do not depend on the speed of the particle, because the speed is much less than the speed of the light, and the fast particles here move in large circles and slow ones in small circles, but all particles with the same charge to mass ratio take the same time, the time period, to complete the round trip, one round trip. And if you analyze the direction of magnetic field, then the direction of rotation for a positive particle is always counterclockwise, and the direction of a negative particle is always clockwise. This the number of revolutions per unit time, which is f is equal to omega over 2 pi. This frequency is independent of the radius of the path, and it is called the cyclotron frequency. In a particle accelerator called cyclotron, and this in cyclotron the particles move in circular paths and given a boost twice each revolution, which and increases the energy of the particle and their orbital radii as well, but their angular speed or frequency don't change. So, and similarly, one type of magnetron, a common source of microwave radiation for microwave ovens and radar systems, emits radiation with a frequency equal to the frequency of circular motion of electrons in a vacuum chamber between the poles of a magnet. So now